When we see bubbles or oil floating on water, you must have seen that in rainy seasons. We see different colors coming out of oil or bubble. Different points have different colors. Why is that? That is due to interference of light. We have understood that light is as wave, it behaves as wave. So what will happen if light behaves as wave? It can interfere with each other. Two waves meet, they can build up or get weakened. So this phenomena, interference, is the reason of why we are seeing different colors from the bubble or oil on water. Now let's say you are walking on a road, it's a rainy season, so some oil is floating on water. Let me draw the diagram here. So let's say this is the oil film. This is exaggerated, it's very, very thin. So that's why we call it thin film interference. So this is very, very thin in reality. It's just for our understanding. I'm just making it this much thick. Okay, let me name the thickness also. So this width, let's say it is T, thickness T. Okay, so you are somewhere here in the air, right? Above the ground. So you're seeing from air. So here's a medium air, oil, and it is, remember, floating on water, rainy seasons. Then only you'll be able to see these different colors when oil is floating on water. Now, why is that only in the rainy seasons we are able to see different colors? Because then the two reflecting surface of oil come into the picture. One is this one, front, and one is this back. If this water is not there, this will not work as a reflecting surface. That's why you will not see interference. Okay, so we understood here is the front portion of the oil film and here is the back portion of oil film. They will work as a reflecting surface. Now, let's see what happens. So here is the sunlight which is coming in this way. It's a white light, remember, white light. So when it will shine on this front portion of the oil film, what can happen? Some of the light will get reflect back and some may enter this film. So let's say this part which I'm showing here, it goes back like this. And let me name it R1. Let me name it R1. So these arrows I'm showing waves. So because if I draw waves, it'll be very complicated. That's why I'm keeping it simple, showing with the arrow, taking the help of the ray diagrams, you can say. So the white light came here, it got reflected back from the front portion, and some part of it go inside. Okay, go inside. And you'll see, oh, again a reflecting surface, right? The back portion of oil comes into the picture and it will reflect back some of the light, right? So let me say this is the reflected wave which has taken this much distance and come back, and now it joins this guy, the reflected wave 1. So here are two waves. One is this one, R1, and one is R2. And if I remove this white light now and bring you here, you are seeing this oil floating on water. This is the eye. The light which you will see now will be the combination of this and this, two waves. Now they are not same. They have a different, may or may not be in the same phase. Why? Just ask this guy is going up. But this guy, R2 wave, it has gone down, covered the distance t, and then came back. So it has taken the extra 2t distance. So there is a path difference between these two waves. We show it by delta x. So it is t plus 2 is equal to 2t. So the path difference of 2t between these R1 and R2 will make all the difference because some wavelength of lights, this path difference can construct them. They can be stronger, and for some wavelength, they can nullify. They will align it crest to trough, so they will get cancelled out. So you will see a different color. You will see only the constructive interfered light here in your eye. You will see the combination of these two waves. They are meeting here, right? So what you will see is not only a single wave, but the interference of these waves. Interference. Now, what kind of interference will happen? That will depend on the path difference these two reflected waves are taking. For example, if you're seeing blue color, if you are seeing blue color at this spot, what does that mean? That somehow these reflected rays, the blue wavelengths have been constructively or become stronger and other have been destroyed. And this will only depend on this path difference, or I can say the thickness in a way. Let's discuss that. Now let's understand why we are seeing different colors. For example, if you see a blue color, why that is happening. So white light, which is shined on the oil surface, is not a single wavelength. It is not a single wave. It is a mixture of different waves with different wavelengths. And we have heard about those. That is our colors: red, orange, yellow, green, blue, indigo, and violet. So the red has the maximum wavelength and the violet has the least. So they all have a different wavelengths. Now, because they are different, they will respond or they will interfere differently for the same path difference. So that is the main point, and we can understand with a simple diagram. Let's see. Think like this. So we have a yellow color light here, so it's a wave, and I've shown it longer because a yellow is longer than, as we are comparing to the blue. Roy G P I V blue is having lesser wavelength than yellow. And now let's take this path difference. So let's say the path difference from here till here. And when the path difference is over, the other wave starts. So this is our first reflected wave, and this is the second one, which is coming covering this path difference, and it is going to join here. So this will be the story with the yellow one. And now here is a blue one, which is covering the same path difference, but remember its wavelength is different, and it is going to join this blue ray. Now what will happen? Let's see. What will happen in the case of yellow and what will happen in the case of blue? Remember, we have kept the path difference same. So I'm going to predict their future. Now, if you see, this wave has to go down, right, and come up like that. So can I say the trough will meet the crest, or they will destroy, or it will be a destructive interference? For the same path difference, what is happening with the blue ray? Let's see. So this will go, there's a shorter wavelength, and now this part has to go up, right? And if you can see here, the crests are matching with the crest, right? They will make it stronger, they will become stronger together. So here it will be constructive interference. So now you got the importance of the path difference. Because the path difference is same, but the wavelengths are different of different colors, some wavelengths will get constructive and some will destroy or become a destructive. So we will see only the constructive interferences which will reach our eye, and we will say, oh, the color is blue. So as of now, let's summarize what we have learned in this video. The first thing is we have learned is different colors on bubble or oil film is due to the interference between two reflected waves. One is coming from the front, other is coming from the back of the oil film. The path difference between these two waves will be 2t, two times the thickness of the film. That also we know. And this is what makes all the difference. As light is made up of different wavelengths, Roy G B I V, for the same path difference, for the same thickness, different wavelengths will interfere differently. Some, they can do constructive interference, and some might do destructive interference. If the blue light constructively interfere, we will see the blue light, and others will cancel out. So this is the summary as of now. So mathematically now we need a relation between the wavelength which will do the constructive interference. So let's say we have two waves. Let's say we have R1 here. One of the reflected ray has a wavelength like somewhat like this. So this is the lambda. So I'm taking lambda from these 2 points. They are also in phase. Now, if this is one of the ray, and let's say the path difference, let's say the other ray is lagging behind. So let's say the path difference is this much. And in this path, if we map the wavelength, so it comes out to be like this. Okay, then it continues like, it will go like this and this. They're similar, just if I've drawn it differently, so please ignore that. So they have to be same. So now if you see the path difference here from here, right? After this, on the right side, they are taking the same path, but on the left, this is the extra path which our reflected ray 2 has taken extra. So if you count that, how much it is this much, right? Or I can say one wavelength is completed, one cycle is completed. And when that happens, we see the crest and trough are meeting, and that's what the condition for constructive interference. So if two reflected waves have the path difference of 1 lambda, then our constructive interference will happen. What if it is 2 lambda? For example, if this path difference is stretched till here, say, and now let's say this much path difference. So I will say the path difference is now 2 lambda, right? 1 lambda here and 1 lambda here. So the path difference between these two waves is 2 lambda. But still, I will get the constructive interference. Crest and trough will meet. So any integer multiple of a wavelength will give us the constructive interference. And mathematically, we can write delta x we represent as the path difference between two waves. And that has to be either it will be 0 or a lambda or 2 lambda or 3 lambda, or a generic expression is m, where m is an integer. So this is one of the equation which can give us the constructive interference. So let me mark it for constructive interference. I will use this formula, constructive interference. So the path difference should be this in these terms. And now for destructive interference, let's see. So I have a wavelength going like this. One is lagging behind. So this is my R1, and from here joins the other line, other wave joins, and it goes like this. Let's say this. So what is the path difference is at this much. Okay, because at this side, if you see, the same path we will take in future, but on this side, this is the extra path it has taken. So the path difference is not lambda now, it is lambda by 2, only half the wavelength. You can say this much distance is lambda by 2. So if the path difference is lambda by 2, see what is happening. Here, the crest is meeting with the trough. And I can continue this, right? I can continue this and you will see that this trough will meet the crest like that. So we will get a destructive interference. They will cancel out each other's effect. They will nullify. So we'll get a destructive interference in this case. So here is a case for a destructive interference. And can it be more than lambda 2 also? Yes. If I increase the wavelength like one wavelength here, yeah, one wavelength here, still I will get a destructive interference. But now the path difference is lambda by 2 plus one wavelength. So it'll be, I can say the path difference is 3 lambda by 2 in a way. So 1 lambda by 2, 2 lambda by 2, and 3 lambda by 2. If that happens, that also it will give me a destructive interference. So similarly, we can build for destructive interference formula like this. I can say delta x in that case will be lambda by 2 or odd number multiple 3 lambda by 2 and 5 lambda by 2. And generic term we can write like m plus 1 by 2 into lambda. So that will be our generic expression. You can put 0 here, so we'll get 1 by 2 into lambda by 2. If you put here 1, you will get 1 plus 1 by 2 or 3 by 2. So 3 by 2 lambda by 2, and you can put likewise different numbers and you can get these values. So done, we have done for the constructive interference what will happen and what will happen with the destructive interference. But here is a catch. What if I flip one of these waves? What will happen in that case? Will these formulas will still work? Let's see. That we need to investigate. So what I'm going to do, for example, let's take a simple example. So here is one wave. Let's say these two waves have no path difference, right? No path difference. So m is equal to 0 in this case. So for constructive interference, we know that m is equal to 0. I should get the constructive interference, right? That is what we have just learned. But what if I flip this one? So what I will do, I will pi shift this. It's a fancy word for that. So I will pi shift that. Just the mirror image I will create. And now what? So this is the flipped one or pi shifted wave. And now if I say what is the path difference, you will say 0. So I should get constructive interference. But in reality, what will happen here, the crest and troughs are matching. So the same formula, the same logic which was giving me constructive interference will end up giving me the formula for destructive interference. And now what about when the constructive interference will happen? Just think, if this is flipped and I keep the path difference of lambda by 2, right? So this is the path difference between these two waves. This one, lambda by 2 only. So now instead of destructive, what I'm getting constructive interference. So this is a big catch. So we need to observe whether one of the ray is getting flipped, one of the wave is getting flipped, pi shifted. If that happens, just flip the formulas too. So let me summarize. Okay, so let me put the formulas here. So we are saying delta x, the path difference, okay, and that path difference will be equal to 0 lambda 2 lambda, and in generic terms I can say m lambda. So it will give me the constructive interference. For that I will use this. Okay, and for destructive interference I'm getting lambda by 2, 3 lambda by 2, and 5 lambda by 2, or m plus 1 by 2 lambda. This is for destructive. So these formulas will work fine in case of when there is no flip, when there is no flip. Okay, like we were doing, like straight away, like both waves are, one wave is going like this, another wave is also going like this. When this is happening, no flip is happening, or both wave flip, so that's the same thing, flipped. So we'll use these formulas. But the major note here is if only one flips, either of them, if only one flips, what we should do? Flip the formulas. Flip the formulas. And this is what becomes the major observation when we are reading questions. So we have to check whether these two reflected beams are, pi shifted, flipped. If only one of them is flipped, flip these formulas. So for the constructive, if one of the wave is flipped, we have to see, for the constructive, we need to see this because formulas are flipped. For destructive, we will use this. And also, we were saying path difference again and again, but in the thin film, what will be the path difference? That will be twice the thickness of the oil film. So instead of delta x, I can put here 2t, right? 2t. So this will give me these two formulas will give me the constructive and destructive interference which wavelengths will have. And also here is a major note, we have learned when to use these formulas. So we know the formulas now, and we also know what to look for. We need to look for the flips. But the question comes here, when the reflected will pi shift or flip, how to know that? So the answer is very, very simple. Whenever you see the light wave is entering a slower medium, the reflected wave will flip. So what do you mean by the slower medium? It's comparatively having higher refractive index. Let's take an example. For example, if I say here is an air, the light ray is coming say from air, okay, and here it enters water. It has higher refractive index, right? The light will slow down. So the part of the ray which will reflect, here is a reflected way. So this reflected way will be flipped. And now there will be third medium also, and we'll see whether that is also flipped or not. If only one of them is flipped, then we will say that the odd number multiple of lambda by 2 will give us the constructive interference. So let's use this logic in our numericals and go forward. So let's attempt our first question. You observe colored rings on a puddle and conclude that there must be an oil slick on the water. You look directly down on the puddle and see a yellow green, and the wavelength what you see is given lambda is equal to 555 nanometer region. You see that region, yellow greenish one. If the refractive index of oil is 1.45 and that of water is 1.33, what is the minimum thickness of oil, the thickness T, that could cause this color? Okay, so first of all, we will draw a diagram. So what is happening here? Here is the oil film. You draw like that, oil film, and N is given 1.45, and then this floating on water, N is given 1.33, and here it is air where we are looking. So the same thing will happen. We will draw the diagram. Here is a white light coming, right? There is a white light coming. Okay, here will come down. First reflection will happen from here. This is our R1, and we need to see whether it is getting flipped or not. So how to know? See, air has refractive index of 1. It is going to enter, our white light is going to enter a slower medium, right? Light will slow down. So whenever the light is entering the slower medium, the reflected ray will flip. So this is the one flip we are having. Okay, so then some part of it has been flipped as R1. Some part of this light will enter here and it will reflect from here, right? So I can show it like this, R2. Now, whether this is flipped or not, let's see. So we need to compare. So the light is about to enter. When it was going here, it was about to enter the faster medium because we are comparing from oil to water. Remember that. Comparatively, this is rarer. We will see the refractive index. We will not see oil or water. We will see the refractive index, and that will tell us whether it is denser or rarer to the light. So here, this is not flipped. Not flipped. Yes, there is no flip here. We are getting the case of one flip. One flip. And when that happens, the odd number multiple of lambda by 2 will give you the constructive interference. So remember that, okay? So because they have asked for a minimum thickness, so we can take lambda by 2. Okay. So this will be our thickness formula. We will use this. Now, they have also given one information. They have given us that you see the light of 555 nanometer. Should I use this lambda here? No, because the wavelength changes when it enters the oil. By how much? We just need to divide this by the refractive index. This is a big catch. So don't put directly lambda in this question as it is given. You need to check whether they have given the wavelength in the oil or not, because this is a thin film interference. The wavelength in this medium will only travel this path. The wavelength changes when it enters to other medium. The lambda here is given, but the lambda in oil is not given. Here, remember these formulas are for oil thin film interference. So this lambda is of oil. But how to calculate that? So here is a side note. We have a formula C is equal to lambda frequency. We will use this. What it formulas tell that speed of light is equal to the just a product of lambda and frequency, and the frequency does not change. See, this does not change whether it is a reflection or a refraction. The frequency of light does not change. So if this guy is not changing and our our speed of light is changing, it is getting less, the same effect will be on the wavelength. So as the speed will get lesser, similar way, the wavelength will also get shorter, smaller. So if somebody asks, light is coming from here to this medium oil, how much it will slow down? So we will just divide it by 1.45. Similar logic, if the wavelength of this in air is this much, 555 nanometer, and I want to check what will be the wavelength here, it will also reduce by how much? I just need to divide by the refractive index. So this is kind of a side note. So this will give us the wavelength in the oil. So here's the catch, you cannot just directly put it here. This is for thin film. Oil, what is the wavelength? Not in the air. Okay, so I will use the calculator from this. Let me use the calculator. That'll be 555 divided by 1.45. So that'll be, I can take 382.76, 76 nanometer. So this is my lambda oil, and I'm going to use it now in the formula. Let me keep the calculator. So from the formula, 2t is equal to lambda by 2. I can simplify it. T is equal to lambda by 4, and lambda here is lambda oil. What is the lambda oil? It is 382.76. Need to divide it by 4, and that will give me, let's ask the calculator, divide this value by 4, and I am getting 95.68, or I can say it 95.7 nanometer. So this is the thickness of the oil slick which you are seeing. That's why you are seeing the yellowish greenish color. The next question is just a repeat, but what they have done is, what if the lambda is not 555, it is 635. It is the red color. So what if you are, seeing this? So similarly, we'll first calculate what is the wavelength in oil, just divided by the refractive index of oil, 665 divided by 1.45, and we'll get this. So this is the lambda oil which we are going to use in the formula, because we have already seen that there is only one flip in this case. So what will happen? 2t will be equal to lambda by 2. The odd number multiple of lambda by 2, the path difference will give you the constructive interference. So I'm just rearrange it. T is equal to lambda by 4, and if you divide it, you will get 109.4 nanometer. It's just a repeat of the previous question. Let's read another question. A glass lens has a non-reflective coating placed on it. If a film of magnesium fluoride, refractive index is 1.38, is placed on the glass which is having a refractive index of 1.52, how thick should be the layer to keep yellow green light from being reflected? So here is the question, not of constructive interference. We want to keep this light to get reflected, so we want to destroy it. We want a destructive interference formula. So let's draw a diagram here. So here is a magnesium fluoride film. This is magnesium fluoride in short. The refractive index given 1.38, and here is our glass below it. So it is applied on that glass, and refractive index is also given 1.52, and here is our air, right? The light will be shown here. So let's see if the white light, comes like this. The first reflected ray will be this with the first reflection. Now let's see whether it will be flipped or not. So it is going to enter here. The reflectance is 1, it is going to enter 1.38. The reflectance is getting more higher, so it will flip. So this will be flipped. So this is my R1, which is flipped. Okay, now some part of this will go inside and reflect back. So this will my R2. R2, whether this will be flipped, let's see. So 1.38, and we are entering to 1.52. Still it is more. So this will be also flipped. So remember that. So these all questions are about flipping, and according to that we will use the formulas. So if both waves are flipped, we can use our formulas which we were keeping, that is delta x. For constructive, we will use the m lambda, or integer multiple of lambda, and for destructive we will use m plus 1 by 2 lambda. That is what we are going to use. And here in this question it is given we need to keep this light from getting reflected, so we are looking for a destructive interference here, not the constructive. Remember that, that's a catch. Okay, so do we know the lambda in air? for yellowish green color is 555 nanometer, but we want to, this lambda will be of this in the magnesium fluoride layer, so we need to put that. So that will be just divided by whatever the refractive index. So that will give you the lambda in magnesium fluoride. Remember that in the formulas we will only use whatever the film wavelength is, not what is given. Okay, maybe they will give this or this also, but in this question they have just told that the yellow green color, so that is in air that has the wavelength of 555 nanometer. You need to change it to get this wavelength in this thin film. Okay, so let me use the calculator here. So let's bring the calculator, and it is 555 divided by 1.38. Okay, so it is 402.2 something. Okay, so it is 402.2 nanometer approx. Okay, and this is the wavelength we are going to use in this formula because we want to destroy this wavelength, or a destructive interference should happen. So the delta x will be 2t, right? Twice the thickness. And then because they are asking the minimum thickness, okay, how thick the shear layer, we can make it any thickness, but we will look for the minimum thickness here. So we can put m is equal to 0, or we can say it'll be equal to lambda by 2. So here we can rearrange it. T is equal to lambda by 4. I have already calculated lambda, which we are going to use is this much. So it'll be 402.2 divided by 4. So if I divide it by 4, I will get 100.5 nanometer. This much thickness should be a layer of magnesium fluoride, so that this wavelength will get destroyed. You will not see this getting reflected. So let's read this question. You can observe thin film interference by dipping a bubble wand into some bubble solution and holding the wand in the air. Correct. What will be the thickness of the thinnest soap film at which we would see a black stripe, or you can say no light, if the light illuminating the film has the wavelength of this much? So this is the source of the light, and we want to see the black stripe. So we will see whether when this wavelength will get destructively interfered, and we have to use the for the bubble, we need to use 1.33 as the refractive index. So let's try to draw a diagram here. So here is the diagram. This is our bubble film, okay, thin film, and here is air. And what will happen to the other side in the bubble? The other side is also air. So if we are shining light, let's see the first one. This is our R1. Will it get flipped? Yeah, it is, because this is 1.33 they have given, and this is 1. This is also 1. So it will be flipped. So 1 is flipped. What about other? It will go this side, reflect ray, and it will reflect here. So this is R2. So now let's see whether it will get flipped or not. No, it will not, because it is going to a faster medium, right? 1.33 into 1, the refractive index is decreasing. So if it decreases, the light will speed up. So it will not flip in that case. So no flip. So we are getting the case of only one flip, right? This is important observation here. This is the main thing of this question. And if it is one flip, then the formulas got flipped also. So for destructive interference, we will use 2t is equal to m lambda, because now it has been flipped. Whatever formula you were using for constructive, that will become for destructive. So this formula which we are going to use, they ask for minimum thickness, so we can take this as 1 lambda, and we can simplify this. Now let's go for the lambda. They have given us in air as 521 nanometer, but we want in this bubble film, so that will be divided by the refractive index of this. So that will be lambda bubble, that will be, let me use the calculator. Here that will be 521 divided by 1.33, and that is 391.73, I can say. 391.73 nanometer. This is the wavelength. Let's put in this formula. So our T will be lambda by 2. Thickness, okay, let me write it here. Thickness will be lambda by 2. 391.73 divided by 2. Let's see what it comes out to be. We will divide this from the calculator by 2 and we will get 195.86. 195.86 nanometer will be the thickness of that bubble film.